introduction now. And I got to be honest, I don't know about you, but to me, phrases like world famous and internationally recognized, I think are overused and overstated when introducing speakers. But ladies and gentlemen, let me tell you, I have definitive proof that Ben Hodges is an internationally recognized speaker. I saw it with my own eyes. It was 2 years ago. I think it was a Tuesday. I was at the Toronto airport and I was there to pick up our keynote speaker for the 53rd International Conference. That was Wayne Huber, who many of you should know. While I was waiting for Wayne's arrival, I, a Canadian citizen, noticed a familiar American, and that's Ben here, who had just arrived from Texas or wherever, and I recognized him right away. So it is with great pleasure that I introduce to you our bona fide, internationally recognized keynote speaker, Dr. Ben Hodges.
Well, thank you for that introduction. I'm rather humbled by it all. But so today, rather than PowerPoint, I'm going to do like I do with my classes, what I've done online is we're going to talk in front of the whiteboard. I'll start with just a little bit of an advertisement. For those of you who've been here the last several years, we've been talking about the Icwmm 5 hydraulics engine, and which we now call Icwmm 5 Plus. The beta release is out, and you'll hear more about that with Eddie Tiernan's talk. This is the GitHub that we are making everything publicly available. And our academic organization, the National Center for Infrastructure Modeling and Management, NCIM, as our contract with EPA is finishing up, has been transferred over into a nonprofit, and that's CIM, the Center for Infrastructure Modeling and Management, and this is the website where you can get to that. So that's all I really want to talk about with the Icwmm 5 Plus. You'll hear more about that later. Glad to talk to anybody offline or anytime about more what we've been doing. But today, I want to use the keynote to think about where things are going, because I've learned a lot as over the past 4 or 5 years as we've been building the Icwmm engine, and I want to kind of talk about where I think things are going. And we're really going to talk about 4 different things here. One is going to be computer CPUs, and another is going to be, so this is just general stuff about computers, data, and we'll talk a little bit about digital twins, the hot thing, a little bit about artificial intelligence, and the ideas of machine learning, and then just some things about where we're going and what we should be kind of looking for as road signs and how the world is changing. So let's start right in with ideas about computers and what computers are doing. So I think of computers as having 4 parts. We have the CPU, we have the bus that connects things together. The CPU is our central processing unit. We have memory, and we have storage. Now, for those of you who were around in the 1980s, one of the things that I would argue that in the 1980s, the CPUs were fast. The bus was slow. Memory was small, and storage was small. That's the sort of environment where a lot of codes were written in the 1980s, and things began to change through the 90s and in the 2000s. But even though by today's standards the CPUs were slow, relative to the bus speeds, anybody remember the parallel printer connectors that you had to have and how slow an RS-232 was? Oh my gosh, the bus connecting things were so slow. We had so little memory in our computers, and our storage, we often ended up dumping data because we just couldn't afford the storage. Well, now, I would argue that despite computers being so much faster, our CPUs are slow. That's why we need a lot of CPUs, because they're slow. We now have fast buses. This is where all the real work has been done over the past 10 to 15 years. CPUs have not gotten faster since 2004. I've talked about that before. The main reason is that to go faster requires way too much energy. In fact, right outside my office, I tried to figure out a way to get my camera to turn around so you could see the big cooling plant that sits outside my office here on the Pickle Research Center that does nothing but serve the Texas Advanced Computing Center and all the supercomputers. But right now, memory is cheap, and we have lots. And the same thing is with storage. Storage is cheap, and we have lots of it. And that changes how we think about and how we write our models, because it's expensive to make computations in a sense. It's fast. We need to be able to move things between our CPUs because we need to use a lot of CPUs. This is where the parallelization has come about and been an absolute requirement. So let's think about where we're going. There's two. This whole thing goes into two things. One is multi-core computers. And this is what you've got on your desk today. Every computer made is a multi-core computer. It's got a chip that will have multiple cores. Each core will have a number of threads capable of doing independent, simultaneous operations. The other big thing is GPU, computers that are made out of graphic processing units. And this is the latest actually in supercomputers. A lot of them, the biggest, fastest supercomputer at Oak Ridge National Laboratory Summit is all a GPU computer. And using multiple GPUs this is a faster way of doing things. So I think that this switch is going to be a sea change that we're going to see happening in the next 10 years. And the reason is simply that GPU computers on the cloud can do, a typical GPU has essentially 4,000 threads in which it can do computations. So GPU computers give us this massively parallel for big problems where, and we want to think about Icwmm using continuous integrated simulation where we're taking real world data. We're either might be going back in time and moving forward and doing what if runs. We want to be able to do Monte Carlo stochastic runs. We want to be able to do big computing. And when we want big computing, we're going to have to go to the cloud. Now, this transition is not necessarily going to be, I don't think you're going to see GPU computers on everybody's desk. Because a GPU doesn't, the standard stuff, whether you're using Word or Excel, GPUs aren't going to help you. In fact, programming to GPUs is a big blockage. But think about what this means for your typical engineering firm. Right now, most engineering firms have multi-core computers that are sitting on engineers' desks. And they're sometimes being used for heavy-duty operations. Sometimes they're just being used to do email. I think that's going to go away. And I think companies are going to save money when it goes away because the average engineer is only going to need a laptop sort of capability, maybe on a bigger screen, whatever, but they're going to need only a simple multi-core because you push to the cloud any big job. That has consequences because once you push a job to the cloud, you know which client that job goes to. You've just changed something that's an indirect cost, the cost of the iron sitting on the engineer's desk. It's now a direct line item charge. So companies are not going to have to invest in GPUs to have around the office because that simply is going to increase their overhead. People are going to go to the cloud. Now, the big question on GPU computers and how well this stuff takes off is the compilers. This, I think, is our a thing that you want to watch out for in the future. When compilers for GPUs get simple, so that and also get standardized. Right now, If you want to program on one manufacturer's GPU, yeah, you got to use their software. If you want to port that to another manufacturer's GPU, you got to use their software. Yeah, so either we get down to one person who makes one company that makes GPUs, or someone's got to standardize the software. Or we're simply not good. That's a big energy barrier of learning how to compile on GPUs. Now, the other thing that may happen is we may get higher level programmers in programming languages, things like Fortran, co-array Fortran, that allow you to not think about the GPUs, that let the compiler and the experts do that. We'll see how that happens, but I think that's a transition that we're going to go through, and we need to be thinking about how to make our models move from, well, right now many models are essentially serial. We need to move them both to multi-core and then be able to jump down to GPU. Yeah, just checking my notes. That's the problem with not teaching, with not using PowerPoint. Is I gotta go back and look at my notes. So, and of course, along this, you can think about is that if you actually had to have both GPU and multi-core computers in your office, the cost then of your infrastructure is really going to go high. And I think that what you're going to see is issues like artificial intelligence and data analytics and getting data, integrating data is all going to make things easier in the cloud. I once heard a presentation by some folks from Google that were talking about it's cheaper for them to do your calculations on their computer, and they'll do that for free because they're required to host data. They've got contracts to host data for on satellites. If you ask to download their data and to do the calculations on your machine, that bus that you use to translate that data is hugely expensive compared to actually doing the calculations. So Google actually gives away on the Google Earth Engine a lot of free calculations to academics rather than having academics ask for the data and download it. And I think that's what's going to be part of the model in the future is how you don't get data. You actually work with the data and will do the calculations. If you want to do calculations on that data, you pay the cloud to do the calculations for you in the same place the data is located. So let's talk some about data. And I think this is, in my mind, the biggest problem that we face within the stormwater industry is data. Because we have data might be collected for one purpose, but we need it for another purpose, translating it between that. Huge problem is simply that the data is expensive to validate, and it's expensive to make this available. So there's a big need for automation in ingestion of data and validation of data. A great example is LiDAR. If you're trying to do a two-dimensional flood model, LiDAR is a great thing for getting your what your landscape looks like. But when you go to try to get LiDAR data, you first find that almost all the state agencies that collect LiDAR, they're really, really interested in collecting LiDAR data. They like flying the planes, they like gathering. They really don't like validating it. It takes forever to validate, and they don't like making interfaces to make it easy. I sort of went in at this thinking, well, I should be able to just go draw a square on a map and get that LiDAR data. Oh, no. You have to find which flights and how they overlap and get which sets of data, and oh no, that's missing on that part. You spend 6 months trying to get a decent LiDAR data set, and still you've got a lot of work to do to validate. Okay, so there's huge amounts of problems with that. And then we have, when we think about the stormwater, which also cities tend to classify stormwater along with their drinking water and think about their data as a security issue. And we've been working 3 months to get an NDA with one city in order to get their a copy of their stormwater system model. It's like these data security issues that mean only certain people can access, which means that nobody gets to work with how do we integrate these data. So we have this problem of we've got lots of data, but we can't connect it well. And I think that's where you hear a lot of stuff about digital twins, the idea of having these seamless models and data that represent what's happening in a city. And I'm skeptical. Okay. And the reason I'm skeptical is simply that there's so much work to be done in linking these models and linking the data in these seamless ways. Who profits? Who is going to fund that? What city? You have to make the case for the city that they will make money or they will save money by building this digital twin. But in many cases, yes, would that give them better models and better information? Yes. But so much of the reason things are done as they are in a city are social political, and improving our models will not improve our social political system. So I think that there's a real problem in making that step to digital twins, but I do think that we have the ability, say, within the stormwater system, to begin looking at how can we build digital twins of the stormwater system and maybe connect with a digital twin of the transportation network. So those sort of things will build up, but I think we're a long way from that. And I think that one of the things that this idea could help us do is to think about how, as we build models and we develop things, we can make a model we build for one purpose within a city be used beyond that and have a life beyond that. We do something for a project. How can that be integrated and developed and maintained within a city to begin the basis of building a digital twin? I don't think digital twins will simply arrive from top level, we're going to build the world. They're going to be built up from the ground. I want to talk a little bit about artificial intelligence and its cousin, probably more like a sibling, machine learning. To be honest, the differences between AI and ML for our practical purposes really don't matter. What we're really talking about that is something that, unfortunately, this stuff has become a buzzword, right? And it's in the research area and a lot of things. It's like, we have to apply AI, we have to apply ML to be on the cutting edge. Okay, yeah, I can see it. The basic idea is all you're doing with AI and ML is you're saying, I have a data set and I want to create a model of that data without understanding anything of the underlying physics, if it's a model of physics, or if it's a social political system without understanding the social political system. You know, you can make the argument that AI and ML is nothing but regression. It's really fancy statistical regression, but it's very useful. And the power of AI is when you can use it to gain new understanding, because you can use the results from that analysis to see connections that you couldn't see when you analyze the data otherwise. The problem with AI is that it depends upon the quality of your data set. And let's just think, for example, in the stormwater world. If we were to take and use all the data that we have about the city of Toronto and all the stormwater information data that's been collected over the years, and we use that to build a model of the stormwater system, and we use that to try to project something in the future, you immediately run into the problem of there will be development in the future. If the development in the future is different than the development in the past, then that model has no validity. It will give you a prediction and you have no idea whether or not that prediction is good. You lose any foundation of uncertainty because you don't have processes underneath it. So this is where I think actually that AI and machine learning have a real good place. It's not going to replace our physics models like Icwmm. Uh, and also people will tell you that, oh, well, AI and ML is more efficient. Well, not really. Because what you can think of is if I have a swim model, right, and I think about this swim model, I'm going to have time. I've got some pre-processing, lots of manpower that I have get involved in this pre-processing. And then I have my model, and my model run is some length of time. So if I think about an AI model of the same machine learning of the same thing, right? What I actually have is a huge pre-processing time, and then it runs really fast. Because what AI and machine learning is doing is it has to train the model, it has to build the model. And this pre-processing is really, really computationally expensive. To do a good job, you have to put this in the cloud. It's just not going to happen otherwise. So yes, you get a model that runs really fast once you've invested in it. The difficulty becomes if you have to keep making the model relearn. Okay, if I want to make some changes to the swim model, I make some changes in my pre-processing, and then the runtime remains about the same. If I start making changes in my data set that I'm using for training, I've got this huge, expensive retraining program that I've got to go through. But all that said, I do think that we have a really great opportunity, and there's in the world of AI and machine learning, there is a thing called PIN. These are physics-informed neural networks. Now, one of the major ways that PIN has been used is in global climate models, where given the resolution that you're working in a three-dimensional model, the turbulence in that and a lot of the subgrid effects like clouds are very difficult. You don't have enough grid resolution. So what they've done is use the physical equations that apply in that grid square to generate a model. And again, the training takes a long time, but once you've trained it, you've got a fast machine learning model that applies in every grid square around the atmosphere. Now, where that works really good is that the turbulence in the atmosphere and the clouds, the physics that drive it are exactly the same everywhere. And the boundary conditions are exactly the same sort of thing everywhere. They're just what's happening in the velocity field. Once you get down to think about the landscape, now you have the problem of, well, do I have to train? If I have some kind of a physics-informed neural network that's supposed to represent the smaller case, I have to train it separately for each section? Yeah, that's probably not going to happen. So this idea, though, it probably can't be used directly. We can't think about subgrid approaches, but we can think about using Icwmm or other models such as Icwmm to make the training data set. That is, if we rely on observed data of a stormwater system in order to build an artificial intelligence model, we'll find that our data is too sparse. But if we use Icwmm as a training data set, we still have all the problems of, well, we've got to build the Icwmm model, we've got to run it enough times to build this data set, we've got to do all this work, but at the end, you have a very rapid AI model, machine learning model, that you can use to model your system. And I think that this is where, when we think about control and control of systems, it's going to be the most effective way of doing control is not going to be control in the Icwmm model. It's going to be control in the AI model that understands the physics of Icwmm. And this is the real value is, if you have put in enough data that understands the physics, then your model will understand the physics. And that's the key, I think, to the future of where we'll go with AI and ML. And so this is we shouldn't just discount AI as it's just the latest trend. It's an interesting trend, and it adds another tool to our toolbox. But we're going to need to be careful of people, as we saw. There was a great presentation yesterday about the Python and how you can use Python for machine learning and AI. And it's really very easy to use these toolboxes, but you can very easily get the wrong answer too. So we have to be very careful with that. And I think one of the places where this also could come into play is in essentially when you want to deal with the 2D nature of flooding and tying a 2D AI model that's well trained to a 1D swim model. That might be one of the most effective ways of using this to speed up overall continuous simulation. So with that as sort of to kind of wrap up where we are, I'd like to think about, well, what's next? And this is really the kind of things we should be looking for and thinking of when we're looking at where are our computers going, where's the cloud going, and one of the first things that we really should do is, and in some ways, what's next is really about what to watch. What should we be looking for? And one of the first things is entertainment. Tech goes with entertainment because entertainment dollars they're spread out, small amount of dollars from lots and lots of people. So why do we have GPU computers? We have GPU computers because GPU processors got really big for gaming. Of course, and now we have GPU computers being used for crypto, right? All the Bitcoin and everything else, that's all GPU. So watching what happens in entertainment and how entertainment drives tech. There's in academia, we talk about the food, energy, water nexus. There's a tech entertainment nexus, right? that these things are connected. And so seeing where that goes will give you a bellwether what's going to happen. What's next in entertainment? I have no idea, right? This is just saying these are things that we could be watching for. I think we ought to watch what's going to happen in crypto. Anyone who looks at Bitcoin and those things can see, this has got to collapse. It is not sustainable. And I always kick myself because when I look back and first heard about crypto, I went, oh yeah, that's just a Ponzi scheme. It's a bubble. Instead of saying, oh, they're starting a Ponzi scheme. I ought to jump in right now because I'll make money. You really make money if you're first in, right? I can kick myself for that. But crypto is interesting because crypto is sitting on a huge number of GPU computers. If crypto crashes tomorrow because regulators cut down on it because of Russian oligarchs using it, then suddenly there's a whole bunch of GPU computers out there, right, that are going to be available. So it could be a little burst that simply makes some machines available to people. Probably won't make a long-term difference. But one of the things that I think that's interesting is coming out of this is what some people have called the information energy nexus. And that is computing things takes a lot of power. Our cloud things take a lot of power, our cloud computers. Well, our cloud computers then, ideally, you place them somewhere near renewable energy. Right? You place them near your wind fields where you've got wind power, and that's great. But what happens when your renewables are cycling offline? If we can place, and this is a thing to watch for, if people start connecting very high speed fiber optics, you have the ability of the investment in the computers is small compared to the investment in the energy. You could have computer centers set at different locations and shift their data over fiber optic backgrounds. So it's just, oh, well, my wind power died over here. I'm going to send it off to where the solar is over there. So that information, being able to switch information in and around will change how the cloud works. And the final thing is watching what happens with data. And this is really watching what Google does. Google keeps investing in data, in collecting data. The Earth Engine is amazing what it can do. How can we leverage Google is something we should be asking ourselves. And a lot of this also, watch to where my hope is that some federal agencies or will step in nations across the world and start developing data validation programs. Because what we really need is data storage and validation that allows us not to spend so much engineer time getting the data, trying to build our model because we're trying to make approximations and understand what's missing in the data. That if those things can be done, it's a huge advantage to how quickly engineering could be done, because once you've got a good data set, building the models are easy. The challenge is always trying to get all the data you need and pull it in. So watching what happens with data, I think, will be a big question for that. So with that, that's my I see my timer's running down to 2 minutes, and so that's about what I've got for today. And again, I do want to warn people on GitHub, the Icwmm 5 Plus hydraulic engine. It is you have to compile it yourself. There is no executable. You have to we've got a Docker set up so that you can get to it. We're still working on some more of the documentation for it, but there's a quick start guide. But that's there for anyone who wants to play around with it. But it's not for the faint of heart. It is not ready for you to apply in your next project. It's ready for you if you want to understand where the Icwmm 5 Plus project is going. Okay, well, I look forward to hearing your questions and talking to you later on. Thanks, everybody.